start recording so I don't forget. As I get more tired, I'll forget the things that I'm supposed to do. Sure. All right, I think we could get started if you just want to take it away.
Okay, thanks. So I have a PhD in computer science, so that gives you a bit of an idea of the perspective I'll have on things. And I have an anecdote to share. So when I was a teenager, about 30 years ago, I remember reading about this field called artificial life, and I read about the Santa Fe Institute, and I naively wrote a letter on paper and sent it to the Santa Fe Institute, and in it I described my as a teenage high school student, and I asked them if they had any pointers to more information about this interesting thing called artificial life. And someone at the SFI actually took the time to reply to me. They found some printed proceedings of her, but these printed proceedings were about an inch thick, and the person put it in an envelope and just sent it to my home address in northern Quebec. So I was very pleased to receive this, and I couldn't understand any of it at the time, but now I find myself for the first time at the ALife conference. So it just goes to show, if you help a stranger, if you help a young person, you never know what will come of it. So I'm going to talk about visualization applied to artificial life. Most of the presentation I'll be talking about visualization. So here are the topics I'll cover. And at the end, what I'll do is I've taken a sample of papers related to artificial life and origins of life, and I've chosen some figures that I can pick on and criticize and talk about how we could improve those. And then I have a few sketches of research for the future of visualization applied to ALife, or how it could help in ALife research. So in the chat, I've shared a link to a Google folder that contains my slides. I've also shared that on the Slack. So the Slack channel for this tutorial is here. Okay, so when visualizing data, I like to think about the type of data that we have, and I like to separate data into two big categories. There's a first category, which I call, maybe we could call it tabular data, and I'll show many examples of that to show what I mean by that. The other big category, which I hope to get to later, is network data. So that includes anything with topology or trees, I would put in that second category. So what do I mean by tabular data? Here's a simple example. I've got, so let's say I'm running a business and I've got sales as a function of year. So I've got this in a table with two columns. One column is sales, that's a function of my year. Now, can someone confirm that you can see my mouse cursor?
I can.
Okay, great. So the sales here you can think of as a dependent variable. It depends on this independent variable. And so I'm going to be calling those two things a measure and a dimension. So a measure, I'm going to use that word to mean a dependent variable. It's a function of a dimension. And so we could describe this data set as a 1D, 1M data set. And now the question is, how do we visualize it? How would we show this data? So maybe you can take a moment to think about how you'd want to show this data. And maybe you'll think of one of the three ways which I'm about to show you. So here's three possibilities. These aren't the only ones, but these are three pretty obvious ones. The graph on the left, I will call a line graph. And in the center, I'm going to call this a bar chart. And then the last one's a pie chart. So it turns out that each of these has some advantage. It also turns out that one of them is recommended in this for this type of data set. So the line chart is actually recommended for this type of data, but each of these charts would be a reasonable choice, and they each have some advantage. The line chart on the left has the advantage that it makes small changes in slope more apparent. And it also suggests to the audience that it could be reasonable to interpolate between your data points. So if you're interested in what the sales were midway between 2 years, you could look at the line to get some idea of that. The bar chart, we could say its advantage is to discourage the audience from doing interpolation, and that might be something that you want to do. The pie chart has the advantage that it tells the audience, all these things I'm showing you add up to some whole. They add up to some 100%. The pie chart also has the disadvantage that it's difficult to compare and to judge small differences in angle. So if you have two sectors of the pie chart that have very similar angles, it's very difficult to see which is bigger. Okay, so I'm putting a green border around the line chart because it's the one that's usually recommended for this type of data, where we have one measure that's a function of one dimension. And the dimension, notice here, is time, right? So let me show you some evidence for some of the claims I just made. I said that small differences in angle are difficult to judge. So here I have three data sets, each being shown as a pie chart and a bar chart. And in the bar charts, it's really obvious that the first data set is increasing, the last one's decreasing, but in the pie charts, it's very difficult to see that. I also said that line charts make it easier to see small changes in slope. So here I have the same data set shown in two different ways. On the right, you can probably see that right here, there's a tiny change in slope, and there again, and there again. But in the bar chart, can you see there's a change of slope here? I can't see that very easily. Okay, here's a second example. This, again, is one measure that's a function of one dimension, but now my dimension is not time. It's this thing I call a region. So imagine we have a chain of stores, and we have stores in the northern region of the country, and the south, the east, the west. And so I have sales as a function of region. This region variable is what we could call a categorical variable. So these are like discrete values of the region variable. And now maybe we don't want to show the data the same way. So how would you show this data if you had to create a chart for this? So the three same possibilities are still possible, but now the line chart would be really misleading, because this line chart would suggest to the audience that it does make sense to interpolate between regions, when really we don't want to be suggesting that to the audience. So the bar chart is what is really recommended for this type of data. So I'll put a green border around that. I've mentioned two kinds of columns in the tables, two kinds of variables. They're either dependent or independent. So they're either measure or dimensions. And just now I was talking about categorical variables. So it turns out there's another way to classify variables into these types. So a continuous variable like time is what I'm going to call quantitative. A categorical variable is like region. So that's where we have these discrete values and there's no natural ordering to the values. So another example of that would be like the countries of the world. Take all of the 200 or so countries of the world, and you could put them in alphabetical order if you like, but that's kind of arbitrary. And if you translate the names of the countries to some other language, the ordering will change, okay? And then in between these two types, we have ordinal variables. So an ordinal variable is discrete, but there is a natural ordering to the levels of the variable. So for example, level of education. Let's say we had data on some sample of the population and we knew if they had completed primary school or high school or a bachelor's or master's degree. Those different levels have a natural ordering, but it doesn't really make sense to say that the master's degree is 50% bigger than the high school diploma or whatever. Okay, so depending on the type of variables we have, whether they are dimensions or measures, whether they're quantitative, ordinal, or categorical, this is going to influence the type of chart that is most appropriate to visualize the data. So here's a third example of a data set. Here we have two measures that are each a function of year. So I've got my sales and my expenses that are a function of year. Let's see. Okay, I see there's activity on the chat. I'm not going to try to monitor that at the moment. So this type of data, there's many ways we could visualize it, and here are a few ways we could do it. The example here we can call an overlapping line chart. We've got grouped bar charts here, stacked bar charts, and here I've got a scatter plot. The scatter plot is a bit peculiar because we're not trying to show the year in this scatter plot, but each of these charts has some advantage. The scatter plot is nice if you're interested in correlations, if you're interested in seeing if there's a correlation between two measures. The stacked bar chart is nice if you're interested in totals, if you want to see the total for each year and maybe compare two different years. However, the stacked bar chart has a disadvantage. If I were to ask you to compare expenses in 2010 versus 2012, if I asked you to estimate the difference in magnitude between those two segments of those bars, it'd be a little bit difficult for you because these two green segments are not at the same baseline. They don't have the same origin. So you sort of have to mentally shift one down to be right beside the other, okay? So when you're comparing these two segments, you're comparing what we call the visual channel of length. And that's a little bit difficult. Whereas on the other hand, in this chart, the grouped bar chart, if I ask you to compare expenses for 2010 and 2012, it's easier, partly because we have better spatial resolution because of the way the y-axis is scaled. But even if they were scaled the same way on y, it would still be easier because in this type of chart, you're comparing with what we call the visual channel of position. You're comparing the positions of the tops of the bars with respect to a common origin, and that makes the task easier. And so on average, the error in your judgment will be smaller when you're asked to compare positions versus lengths. Okay, so I was just talking about visual channels. There's a whole list of visual channels that we can make, and we can order these visual channels according to how effective they are at communicating a quantitative value. So position, it turns out, is the best visual channel for communicating a quantity. And so again, this has been confirmed in studies where people have been asked to estimate the difference in magnitude between two, for example, the heights of two bars, where people have to compare the positions of the tops of the bars with respect to a common origin. And so this is the visual channel that's being compared in a bar chart, in a group bar chart, if you're asked to compare the red and the blue. In second place is length. So if you were to ask people to compare and estimate the difference in magnitude between the red and the blue here, there'd be a little bit more error in their judgment on average because it's a little bit more difficult. In third place in the hierarchy is angle. So if I were to ask you what's the difference in magnitude between these two angles in a pie chart, that's even more difficult. Your error on average will be higher. And then things get progressively more difficult as we move down this hierarchy. So judging differences in area is even more difficult. And then color value, or what we might call color lightness, it's a little bit more difficult. Saturation, very similar. So value and saturation I put in the same box here. I don't actually know if there have been studies comparing these two, but these two are very similar in difficulty, and they're a little bit more difficult than area. And then even more difficult, even worse would be like comparing the volume of two three-dimensional objects, or color hue is really bad. So if you use a rainbow spectrum, which is very often used in scientific visualization, if you're asked to estimate the difference in magnitude between two hues, that's quite difficult. And shape is also very difficult, okay? So this hierarchy can be used to justify choices of how to visualize information. As a designer, we can say, I want to make use of the channels that are the most effective to show the variables that are the most important to answer whatever questions I might have about the data. And this entire hierarchy I've just shown you is only valid for quantitative variables, like time or something continuous. It turns out if you have an ordinal variable, the hierarchy changes. So I've got a message saying my internet connection is unstable. If you can't hear me, just yell, and maybe I'll try to investigate. So the hierarchy, okay, thank you. So the hierarchies depend on the type of variable you have. And take a look at color hue. Color hue is like a hue of the rainbow. It's pretty bad for visualizing quantitative variable, but it's pretty good if you have something categorical. Imagine you want to visualize the different departments in a university. Maybe you have like 5 departments. Let's imagine a very small university with 5 departments. You could assign each department a color, like very easy for someone to look for orange or look for red, whatever department they're interested in. Okay, here's another example data set. I've got sales as a function of both year and region. So within each year, I've got my 4 regions. So I've got one measure, which is a function of 2 dimensions. How could we visualize this data? Take a moment to think about that. Okay, so one way is with overlapping line charts. We could use stacked line charts if we're interested in totals for each year. We could also use stacked bar charts, again, if we're interested in totals. We could use grouped bar charts. This is grouped by region, and this one's grouped by year. Another possibility, maybe some of you thought of this, is a 3D bar chart. And people in the field of visualization like to hate 3D bar charts. They're considered kind of kitschy. As you can see in this case, there's problems with occlusion. A lot of the bars are partially hidden, so it's difficult to judge. This data, which maybe aren't so obvious, are with what I would call a heat map, and the one on the bottom here could be called parallel bar charts. And it turns out you can make this pretty easily in Excel. In fact, I think everything here was made in Excel. The parallel bar charts you can make in Excel with something called conditional formatting. And in Google Sheets, there's something similar called spark lines, which allows you to do this. So the heat map and the parallel bar charts, one advantage they have over the ones on the upper half of the slide is that I don't need to choose a color palette. I can just use, in the case of the heat map, I chose green, my single color. Parallel bar charts, I didn't even need any color for that. I can also put text over the cells, and this gives me sort of a combination of the advantage of the visual and the text. So the visual part is great, values are big, which ones are small, what the trends are, and having the text on top allows me to read detailed information. So this is it's great if you can add text labels on top of your visualizations. The heat map, if we think about the hierarchy of channels I showed you earlier, the heat map does have the disadvantage that it's making use of colors. So it's not so great in terms of this hierarchy, but it does scale up very nicely to a large number of regions and years. In the limit, you could imagine having a single pixel for each of these cells and it would still be intelligible. But don't use 3D bar charts. Okay, so this is just a summary of what I've just said. I'll just skip this in interest of time. Here's another example of a tabular data set. And so this is an example I made up to make it look more like what we might see in a database. So I'm running a store, a music store. I sell musical instruments to my clients. Here are the names of my clients, what they bought, how much they bought it for, the date they bought this at. Question for you, which of the columns in this table are dimensions and which ones are measures? So remember, measures are a function of dimensions. So a dimension would be something that allows me to uniquely identify a row. And it turns out that in this case, there is no dimension. All of these columns are measures. If I wanted to, I could add an extra column. Maybe I would call it primary key or index or something, and then I could give a unique number or a unique ID to each row, and that would be my dimension. Something else to notice is this table can be thought of as a relation in the mathematical sense. So imagine the set of all possible client names, and then the set of all possible products that were bought, and the set of all possible prices, the set of all possible dates. You have all these sets, then form the Cartesian product of those sets. So you end up with this big space, right, of tuples. What this table is doing is it's enumerating certain tuples within that big Cartesian product. So the table determines a subset of a Cartesian product. And in that sense, it is a relation. And that's why we talk about relational databases, because each of the tables is a relation. It is a subset of a Cartesian product. So we could call this tabular data, we could call it relational data. Sometimes it's called multidimensional multivariate data or MDMV data. That acronym isn't used very much in the literature, but some people use that acronym. Okay, another example, imagine you have a video made up of a sequence of frames, and within each frame we have a bunch of columns and rows of pixels. Each pixel has a color with red, green, blue components. You can imagine taking each of those pixels and listing them as a row in a big table, right? So in my table I would have X and Y and the time of the frame, and then I'd have the components of the color of that pixel. This might sound like a strange way to represent a video, but you could do this if you wanted to. And then you could ask, well, which of my columns are dimensions and which ones are measures? So in this example, my dimensions are X and Y and time, because once I choose an X, a Y, and a time, I uniquely identify some row and I can look up the red, green, blue. So red, green, blue are measures. They are a function of X, Y, and time. And it's up to us as a designer to choose how we want to visualize this data. So one way we could visualize it is like this, a sequence of frames. Maybe the frames are shown one after another in an animation, or maybe they're shown side by side as a static strip of frames. Another way to imagine, another mapping that we might imagine is as a volume. And there are people who have done research on visualizing video as volumes, as space-time blocks. Another mapping that's possible, this might seem weird, but we could plot a 3D scatter plot of the pixels. We'd have an axis for each color component, and we could start placing each of the pixels one by one in this scatter plot. And this might be weird, it might not be useful, but it is a valid mapping. So my point is that as a designer, it's up to you to choose how you're going to map the variables in the data to the axes in your visualization, okay? So one way to imagine visualization is that you have a data set on the left, and it might have many variables. Some of them are dimensions, some of them are measures. They might be quantitative, ordinal, categorical. It's up to you as a designer to choose some mapping that sort of projects this down into, at most, 3 spatial dimensions. Often we just want 2. Maybe there's 1 temporal dimension for an animation if you're using that. So it seems like the problem is it seems like we have a lot of constraints that we have to work within, okay? But happily, we do have several visual channels that we can leverage. And there are also ways I'll show you to use spatial axes for multiple variables at once. Okay, so what are some examples of ways we can visualize many variables at once? I've already shown you some hints of how to do that with parallel bar charts and heat maps. Another way we can show many variables at once is with something called a glyph. And there are other techniques I'll get to later on, but for now, let's just talk about glyphs for a moment. So one of the earliest glyphs that were proposed were Chernoff faces. The idea of a glyph is it's a little picture, a little graphic that has several parameters that can be mapped to different variables in your data set. And in this case, someone decided to take information about different drugs and map those to different parts of these faces. And so we get a little picture summarizing each of these drugs and their effects. A glyph doesn't have to be a face. It could be anything. So here I've got aeroglyphs. And you've probably seen these visualizations of vector fields or wind, where you have a grid, a discrete grid of points. And for each point, we draw an arrow showing the direction and the speed of the wind. In this case, the researchers were interested in also showing the uncertainty in direction and the uncertainty in speed. So they played with different visual designs for glyphs that would show direction, speed, and uncertainty. And we could ask ourselves, if we think of the data in terms of a table, what would the columns be? And which variables would be dimensions, which one would be measures? So it turns out that in this case, there'd be 2 dimensions. There'd be latitude and longitude, or if you like, y and x, those are the 2 dimensions. And then the measures would be direction, speed, uncertainty in direction, and uncertainty in speed. Another example of glyphs, candlestick charts. You may have seen this with financial data. So here's a stock price changing day to day. Each candle shows the opening and closing price, so the price of the stock at the start and at the end of the day. And the wicks, the little line segments above and below each candle, show the min and the max price of the stock throughout that day. So our horizontal axis is the date, and then and the color, I forgot to mention, the color of the candlestick shows whether the price rose or fell during the day. So this is another example of a glyph. Glyphs can be all sorts of things. You can make up your own glyphs. You can even make little charts and sort of shrink them down and they become a glyph. So each of these bars could show a different parameter of something you're interested in visualizing. Another example, here the countries of the world are being visualized. So we have life expectancy vertically. Horizontally, we've got the GDP per capita. So how much money or how much each person is being productive. Each country is a disk. The diameter shows the population. The color shows the region of the world. And there's a way to animate this. There's like a button you can press to play the animation, and you can see the countries moving throughout time. And if you haven't seen him already, Hans Rosling is a statistician who passed away a few years ago, and he gave some excellent TED Talks where he has graphics like this, and he uses them to tell stories about the last few decades of development of countries in the world. Okay, so the 3 examples I just showed you, it's interesting to notice what's going on with the axes. In this most recent example, both axes were measures. Whereas in the example with the vector field, both of them were dimensions. And in the example with the candlestick charts, we had a measure as a function of a dimension. So it turns out that glyphs are good at showing measures. You can always add more handles or more parameters to your turn-off faces or your arrows. You can add little things hanging off the glyph if you want to show more measures. That's pretty easy. But it's difficult to show more than 2 dimensions at once. So that's a limitation of glyphs. So here's another strategy for showing many variables at once. And at the same time, it'll be an example of how we can play with mappings. So Tableau is this very interesting piece of software where you can load up a CSV file or a spreadsheet, or you can connect to a database. Tableau will suck in all the data. It has heuristics to automatically determine which columns are dimensions and which ones are measures. If it makes a mistake, you can drag and drop between these 2 zones to correct its mistake. And then you can drag and drop these variables into all these zones here. And depending on what you drop and where, it will automatically choose the appropriate chart for you. So it can support line charts, bar charts, stacked bar charts. It has a feature called Show Me, where you can easily switch to a different view of the data. And the mapping that's chosen for you is always pretty intelligent and useful. It can show data on top of a geographic map. So here's one example I'd like to dig into a little bit more in detail. What's happened here is 4 variables have been dragged by the user from the dimensions and measures and dropped up here. And you'll see there's one row here that's called columns. Another one's called rows. So the columns, you see in the visualization being shown, there's 3 big columns. And those are central, east, and west. That's what's being called region here. So this region is a categorical variable with these 3 values. And then within each column, there's the weekday. That's what's being shown here, Sunday through Saturday. Okay. Then look at the rows. There's 3 big rows, and those are home office, corporate, consumer. That's the market segment that's been dropped here. And then within each row, there's a vertical axis here for the sum of sales total. That's what we've got here. Okay. So maybe you see the idea that the user can drop any number of variables into columns and rows. And what happens is the space here is recursively subdivided to make room for all the charts that are necessary. And the charts that end up being shown within each cell depend on the type of variables you have here at the very end. So in this case, blue is a dimension, green is a measure. If you have a measure as a function of dimension, you get line chart or bar chart. In another case, if you have measure versus measure, you end up with a scatter plot. And I think if you put dimension versus dimension, you'll end up with a crosstab or some other chart. So this strategy of subdividing space to make room for multiple axes, multiple variables along one spatial axis, this is something we could call dimensional stacking. It's another way to show multiple variables. Okay, so here's a little exercise for those of you who would like to spend some time thinking about this. Imagine you're given a table of data about cars. And this is an example I got from an old article, so maybe the models of cars are going to sound old to people who know about cars. I don't know much about cars. But you have a table listing 19 models of cars, and there's 5 columns in this table. The first column tells you the model of car. The second column tells you the price. Then you have the mileage, the repair record, and the weight of the car. And you'd like to visualize this data. And in particular, you're interested in visualizing the price and the mileage, because those are the things that are going to influence, most of all, your decision on what car you want to buy. So it'd be great if you could come up with a way to visualize all 5 of these variables at once. But at the very least, you should visualize these 2 variables, the price and the mileage. How would you do that? So maybe we can spend 3 minutes thinking about that, those of you who would like to, and I will check the chat window. Okay, so most recent comment, Austin Marcus, yes, dimension is the car model. Susan Stephanie, parallel coordinates, great. I will get to those later. Taylor is asking, in a group bar chart, how should we group things? And what is the effect on perception? Let me see. Well, I'm thinking off the top of my head here, but bars that are closer together are easier to compare. So depending on what type of comparison is more important to you, I think that could be used to justify one choice of grouping over another. And we have someone suggesting a way to visualize the data. So before I read that, there were some longer comments earlier about pie charts. There could very well be cases where pie charts are well justified. I'd have to look at this article that Emily has linked to. It may very well be that there are cases where a pie chart is good. The only reason I can think of to use a pie chart is if you really want to communicate the message that all the sectors you're showing add up to some whole, that you're showing the decomposition of 100% into these parts. Okay, so Jan Kim suggests X for price, Y for mileage. Repair could be a grayscale. Weight could be a dot or circle size. That's great. Jan Kim's suggestion is great. That suggestion is not the only good solution, but it's great. And whenever I give this exercise to students, there's always some students who come up with that solution because it is one of the best solutions. So I'm going to minimize the chat. I'm going to see if I can switch to the end of my slides. So I didn't come up with this exercise. It's an exercise I got from an article from 1986. So it's kind of old. But that article gives two possible solutions. And one here on the left, I think, is the one that Jan Kim just suggested. And maybe some other of you have also thought of it. So the idea is we use the axes for price and mileage because price and mileage are the most important variables. So we should use the position channel to show them, right? And then, let's see, in this case, repair record is an ordinal variable, isn't it? So any channel that is reasonably good at showing an ordinal variable is fine. Weight, I guess weight is a quantitative variable, so maybe area is a better choice than color, and color is a reasonably good choice for an ordinal variable. So this is fine, and I mean there are variations of this that would be possible too. Because there's only 19 models of car, you could even imagine adding the labels, the names of each car beside each point. That would be very feasible. Another way to do it is with parallel bar charts. And maybe this has the advantage that you have more detailed information about each of the values, but it's a little bit more difficult to see each car as a whole, or it's more difficult to get a quick overview of the entire data set. Whereas the graph on the left, you do get an immediate overview of the data. You can see there's sort of a trade-off, isn't there? It looks like there's a trade-off between price and mileage, and that's pretty easy to see here. And when I give this exercise to students, there's always some students who come up with these really creative solutions. But anyways, these are two solutions that are quite good. Okay, so thank you for indulging me with that. Now, where were we? Here. So back to techniques for showing many variables at once. We talked about glyphs. Dimensional stacking, that's the approach in Tableau where space is recursively subdivided. Parallel coordinates, so I think Susan mentioned this. And another technique which I like is the scatterplot matrix. Sometimes people call this the SPLOM. So I will show you what these two things are. There are also other techniques which I won't discuss. And I think these are called dimensional reduction techniques. So PCA, MDS. And if you follow the machine learning literature, maybe you've seen this thing called T-SNE mentioned. So these are techniques which I'm happy to discuss in question period, but I haven't got any slides to explain them. So parallel coordinates, here's another example of a data set. Let's say we have a bunch of students and they're all taking these 4 courses. We have the marks of the student in each course. So each student is like a row or a tuple. Okay, so the courses are physics, math, French lit, and history. The idea of parallel coordinates is you simply have a vertical axis for each measure, or each course in this case. And then one student becomes a polygonal line that intersects each of those axes at the appropriate position. So this is one student doing well in physics and math, not doing so well in French, Lit, and history. Here's a second student in red, and this person's having difficulty with physics and math, but is doing great with French, Lit, and history, okay? The scatterplot matrix is another way to show this same information. So in the scatterplot matrix, the idea is that you show a scatterplot corresponding to every pair of courses, or more generally, every pair of measures. So here I have math versus physics, French Lit versus physics, and so on. And each student, I've got one student here, becomes a single point in each scatterplot. So there's my one student. My second student is in red, so that's where that person is, okay? And we can add a whole bunch of students. Here's another example. Now I've got 4 slightly different courses. I've got 5 students. One of them is in red, one of them is blue. And on the right is parallel coordinates. On the left, you have a full matrix. So this is why we call it a scatterplot matrix, because we're taking all of our variables and crossing them with themselves, and it produces a full matrix. But this matrix, we don't actually have to show the whole matrix because the matrix is symmetric, right? Look at this scatterplot. This is math versus dance. Well, that's the same thing as dance versus math. Where is it? Dance versus math, sorry. So these two scatterplots, these are redundant. Math versus dance, dance versus math. This is a symmetric matrix. I could just get rid of the upper triangular half, and I can also get rid of the diagonal, because the diagonal just shows each variable with respect to itself, so it's not very interesting. So here's an example of a SPLOM showing some car data. We have a whole bunch of cars, miles per gallon, number of cylinders, displacement, horsepower, weight, and so on. You can quickly scan this and you can look for correlations, like there's a correlation between weight and horsepower. That's not surprising. Maybe there's some outliers that might be interesting to look at that are not on this correlation or not on the sort of trend. Another example, these are some seashells. So here, the person who made this is only showing the lower triangular half, and they use the diagonal to show the names of the variables. So we got the sex, the length, the diameter, the height, a whole bunch of measurements of each shell. And again, you can look at this and you might be interested in correlations or inverse correlations or outliers and so on. Another example, these are again automobiles shown, it's the same data set shown 2 different ways. So scatterplot matrix, in this case, instead of showing the scatterplots along the diagonal, they decide to show histograms. So that's a better use of the diagonal. And parallel coordinates on the right, the tuples are colored according to number of cylinders in the engine. Okay, so here's a summary of what I've shown you. On the left, we have some simple cases of simple data sets, and there's a variety of ways of displaying those. On the right, we have some more complicated data sets where you have many variables that you want to look at the same time. And I showed some strategies for dealing with that. Each of these strategies has some limitations. So dimensional stacking, maybe you could get away with showing up to roughly 6 dimensions or 4 measures or something around that range. But eventually, you run into this problem where the amount of space required just explodes, because every time you add another dimension, you multiply the amount of space required. The glyphs and parallel coordinates and scatterplot matrix, those are fine for showing many measures, but they don't work so well for showing many dimensions. So that's sort of a limitation with them. If you have many dimensions that you want to visualize, here's a little advertisement for some work that we've done. We propose something called the generalized plot matrix, which scales up better to a larger number of dimensions. I might have time to show you that at the end, but if not, there's a video there that shows that. Okay, a few words about color. So you may know that on most humans' retinas, there's 3 types of cones, and each of them is tuned to a different frequency of light. And that's why we have this notion of 3 primary colors, okay? If you went through preschool like I did, you were taught that the 3 primary colors are red, yellow, and blue. That red, yellow, blue, that it comes from a tradition in art, and for all I know, it's a tradition that's centuries old. It turns out to only be approximately true. Today, with our modern understanding of color, we know that if you're mixing light, like on a computer screen, it's better to use red, green, and blue This is a better set of primary colors. Here I'm referring to primaries for an additive system where when you mix two colors, the mixture shows you the frequencies that were in each of the components. Okay, so if you mix all three, you get white. On the other hand, if you're mixing paint or ink, the mixtures work differently. They work subtractively. So a mixture will absorb all of the frequencies absorbed by the components. And when you mix all three, in theory, you should get black. And so the primary colors are different. And maybe you've noticed that when you buy ink for your printer, you buy CMY ink. Okay, so the primary colors for a subtractive system are different. But we're going to talk about additive colors. And while I'm showing you these response curves of cones, I'll mention a bit about color blindness. So there's several types of color blindness. Most often what's going on is there's some allele of some gene which is affecting the green or the red response curve here. And it turns out that those two genes are located on the X chromosome. And you know, women have 2 X chromosomes, men have 1. So in some sense, women have a backup. If you have one of these alleles that causes a photoreceptor to be absent or to have a different response curve, it's a recessive allele. So if you're a woman, chances are on your other X chromosome, you've got a dominant allele that will prevent you from being colorblind. And so that's why colorblindness is so much more common in men. It affects about 8% of men and something like 0.5 to 1% of women. And so what happens most of the time is one of these curves is absent or it's been shifted closer to the other one. So if you imagine an allele that causes the green to be shifted towards the red or vice versa, the effect of that is the person will have more difficulty distinguishing red and green. So that's why the most common form of colorblindness is a difficulty to distinguish red and green. So it's good to keep that in mind when we're choosing colors. Colors can be organized in a color space. So maybe you're familiar with red, green, blue color space. So each axis is one primary color. Another color space that's really useful is hue saturation value, or HSV. So imagine a cone. The center axis of that cone passes through all shades of gray, from black to white. Okay, so our position in height is called value. And then as we move away from that central axis, we get colors that are more and more saturated. And here's a top view of that cone. So a color that's very desaturated is going to look more, it's going to look closer to gray. So it's what I'm going to call a pastel. A pastel color is simply desaturated. It's been moved closer to white or to gray. Okay, so it turns out that on our retinas, we have a lot fewer blue cones than other types of cones. And close to the fovea, there's almost no blue cones. So maybe you've seen these illusions where you fixate a blue dot on a white background. And if you stare at the dot long enough, it disappears. So that's because there's no blue cones on your fovea. And to make things worse, as we get older, the lens in our eye yellows. So it absorbs more blue light and that makes us even less sensitive to blue. So this is an explanation for why you should never put small blue things on a black background. They're very hard to see. So here, I don't know if you can see this text, but it says never put blue text on a black background. And for the same reason, you shouldn't put yellow on white, because the difference between yellow and white is in the blue component, right? Yellow is a mixture of red and green. White is a mixture of red, green, and blue. The only difference between the two is in the blue component, and that's why yellow is hard to see on white. And so other combinations of color that only differ in blue are also difficult to distinguish. So you should never put yellow on white, yellow text on white, or yellow lines or yellow dots on white. You shouldn't do that. Same thing for blue on black, red on magenta, cyan on green. So please prepare your eyes for something unpleasant to look at. Here are those combinations. Maybe this will give you bad dreams. I don't think I've ever seen people put red on magenta or cyan on green, but I have seen people put yellow on white and blue on black, even in published academic papers, and I can show you examples of that. So that's maybe one guideline to keep in mind. Another one is try to use desaturated colors for large areas. So use pastels for large areas, and for small details like points or lines, thin lines or text, use colors that are more saturated. Okay, so here, the small thin objects are more saturated, the larger areas are pastel. This is the opposite, you shouldn't do this. Next, if you're using color to show a categorical variable, so you need to choose a different color for each category, it's preferable to use colors that have easy to remember names. And so I think in almost all languages, these colors all have simple names, right? Red, green, yellow, blue, black, white, pink, orange, brown, gray. This one we could call cyan or turquoise or something, and this one maybe we call it purple or something like that. Every one of these has a simple one-word name, and that makes it easier to remember the color code. On the right, this is an example I found this morning where the countries are colored according to the type of government. And it looks like we've got 4 shades of blue and at least 2 shades of orange. So this is going to make it more difficult for someone to remember which color is presidential, constitutional, republic. So you should avoid doing this for a categorical variable. Other things to keep in mind, if you're choosing a color palette for coding thin lines or dots, I would encourage you to try doing it on a 50% gray background, because I think it makes it easier to find distinct colors, and I'll show you an example of that. And also keep in mind, something like 8% of men are colorblind. Most of the time it's difficulty with red-green. So if you are using red-green in your visualization or in your charts, it's nice if you can offer some interactive choice to switch color palettes. For example, yellow-blue is very easy to distinguish if someone is red-green colorblind. And then if you're using color to show a quantitative variable, avoid using rainbow spectra. Instead, use something that only changes one component of the color, maybe with a discontinuity somewhere to show where 0 is. And I'll show examples of that. Okay, so I've been involved with several projects with students where we had to choose colors to code thin lines in some visualization. And every time it was a pain in the butt. And so I finally sat down and I tried to get systematic about it. And I said, what if I just try every combination of foreground color on every possible background color? So what you have here is I've varied the red, green, and blue components to be either 100 or 50 or 0% in all combinations. So I think that's 27 different foreground colors. And I played with 5 different background colors. And I'm convinced that I can squeeze a little bit more out of this. I can choose a few more distinct foreground colors if I use a 50% background color. And so here's an example of this where I got a 50% background color and I've chosen 10 different foreground colors that each have a unique name that's easy to remember, and they all look pretty easy to distinguish. This is actually not easy to do. If anyone thinks they can do this on a white background or a black background, I challenge you, and please share your color palettes with us on the Slack channel. So here I'm drawing thin lines. Here I'm drawing regions with some transparency. I forget what alpha value I was using here. I could look it up if anyone wants to know. So there are various articles warning people to not use rainbow spectra when visualizing quantitative variables. Here's an example on the left. These rainbow spectra are very common in scientific articles, but they're bad. And you can see here, one reason it's bad is because this is the same map. It's the same data, by the way. Here you cannot see the coast of Florida, but you see other things. Maybe those other boundaries are just artifacts of the spectrum you're using. What's being done on the right is there's a spectrum that was chosen where only one color component is being varied, and there's a discontinuity at 0, so it makes it easy to see where the coast is. And there are studies that have been done, perceptual studies. People are asked to judge and estimate the difference in magnitude between 2 different colors, and they do better on these types of scales than on rainbow spectra. Other reasons you don't want to use a rainbow spectrum is it creates artifacts. Like look at these 2 data sets. It's the same data. On the right, it looks like there's a boundary from red to yellow, and again, yellow to green, but those boundaries aren't really there. They are not part of the data. The data varies very smoothly. Another difficulty is yellow and green. Which one is closer to red? Now, if you take a moment to think about it, it'll be clear that, okay, green is closer to blue and yellow is closer to red, if you're familiar with the rainbow and the ordering of colors. But it takes a moment to remember that. And if you're just looking at some visualization where there's a whole bunch of colors, it's not immediately obvious whether yellow or green is bigger in value. Whereas if you use a spectrum like this, it is immediately obvious which shade of color is bigger or smaller. And just a passing message, if any of you are colorblind or you know someone who is colorblind, you probably do. There's an interesting new technology. It's a type of filter that was discovered accidentally. And what it does is it blocks some of the overlap between these response curves, and it can help certain people with color blindness to more easily distinguish certain colors. These glasses are not cheap. They cost up to $600 US, but it might be good to know about this. Okay, how am I doing for time?
You're doing pretty well, I think.
Okay.
Quite a bit of time.
So the next sections are more short. So I'll talk a little bit about how to visualize network data and trees. It turns out there's an entire area of research on how to visualize networks, or what are called graphs in discrete math. There's this whole area of research called graph drawing. And graph drawing sort of grew out of computational geometry. They have an annual conference called Graph Drawing. I think it's called the International Symposium on Graph Drawing. There's several books now that have been written about graph drawing algorithms. And these algorithms can produce very nice layouts of networks. Unfortunately, they're usually quite complicated to program. And usually a graduate student cannot understand an algorithm just by reading one paper. They might have to read several papers. So what you can do instead is use a software package that already has an implementation of an algorithm for you. Or there are also certain layout algorithms that are quite easy to program. And one of them, which is very popular, is force-directed layout. So the idea here is that you treat the network as if it's a bunch of masses connected by springs, and you're simulating forces between the masses, and you're hoping that as the simulation proceeds, the nodes will eventually converge to some final positions. So I actually have a demonstration of this somewhere. Maybe it's here if I'm lucky. Yeah, here. I'll move this over a bit. So this is the JavaScript implementation of a force-directed layout. I'll hit reload to start over. And I can click on one of these nodes and tug on it with my mouse. So what's happening is there's a loop, and for each iteration of the loop, the code is computing the effect of two forces on each node. There's one force, which is a repulsive force that pushes all the nodes away from each other. There's another force, which is a spring force, and it's trying to make the neighboring nodes stay at a certain distance between each other. So these forces are computed for each time step, for each iteration of the loop. We find the net force acting on each node, and then we move each node a little bit in the direction of that force. And then a problem that comes up is, how do you choose the time step? If you make the time step too small, like I'm doing here, well, then the algorithm is very slow. It takes a long time to converge. Okay, so if I just re-randomize the network, I have a small time step, it takes a long time to converge to anything. On the other hand, if I put the time step too high, things become unstable, because the nodes end up being moved too far at each time step. And so you end up with these oscillations or these vibrations. And this is sort of a problem that comes up whenever someone tries to program one of these things for the first time. And there's different solutions that are possible. Like you could use something like simulated annealing, where you, over time, you slowly reduce the size of the time step, and there's other things that you can do. But I was very happy when I learned that there's one algorithm which is incredibly effective. It's almost unbelievably effective, and it's surprisingly easy to implement, and it's not widely known. And it's called stress majorization. So, you know, I'm not super knowledgeable about math. Maybe some of you have heard of stress majorization already, but there's a paper that describes how to use stress majorization to do network layout, to do graph layout. And the article that describes it is a little bit intimidating, because, so I've read through it. There's a bunch of math in the beginning, and it's a bit difficult to understand. But then when you get to equation 12 in this paper, the authors say something surprising. They basically say, it turns out you can ignore everything we said up to this point and just implement this equation number 12, and it probably will work. They wrote this as if they didn't even try equation number 12. I did, and it works great. It's really easy to implement. So there's some details here if you're interested. So the advantage of this approach is that you don't have any oscillation. You don't have any instability. It's guaranteed to converge. It won't necessarily converge to a global maximum or global optimum, but it will converge, and it does it surprisingly fast, and you don't need to choose any time step. Okay, so that's good to know if you are interested in force-directed layout. Another layout algorithm that's easy to program is arc diagrams. So you take all the nodes in your graph or your network and you lay them out on a single line, and then you draw the edges as arcs. And because you're using arcs, it's usually pretty easy to distinguish the edges. You can save space by making the arcs cover a smaller angle. And then you can also use the perpendicular direction to show some other information, like maybe you want to show little glyphs, or maybe line charts, or maybe you want to show something about the evolution of these nodes over time. So you have that horizontal direction available to you to do that. There's also different algorithms to order these nodes to reduce the average length of the arcs. So here in the leftmost image, I have random ordering. On the right, I have the same network, but now I've ordered it according to something called the Berry Center heuristic. And I have an article that describes how to program that. It's surprisingly simple. Another technique that people have played with is using adjacency matrices to visualize networks. So here I have the same network shown as a node link diagram and as a matrix. So every node here corresponds to some row and some column in the matrix, and a cell is filled in if the two nodes are adjacent. Here, the ordering of rows and columns is random. And here I have the same network after reordering things according to the Berry Center heuristic. And what happens is that the edges end up clustering along the diagonal, and there are certain blocks that become apparent. These blocks correspond to subgraphs of a particular structure. And I have a slide showing what's going on there. So here we have our adjacency matrix where things have been ordered according to Berry Center heuristic. When you see blocks like the ones in green, that corresponds to something called a biclique, and the ones in red correspond to cliques. And if you see another region that's mostly filled in, that's a cluster. So these adjacency matrices are kind of a weird way to show a graph, but they have the advantage of not suffering from any occlusion of edges. There's no overlapping edges in one of these matrices. And you can also sometimes see interesting structures along the diagonal. You can also add arcs along the sides of the matrix to make it easier to see pathways that connect nodes. So I have an article which gives a tutorial on how to implement these different layout algorithms, how to order the nodes, and there's I think there's about 70 references in the bibliography, so that can be an entry point to people who are interested in programming their own network layout algorithms. Visualizing trees. So trees we can think of as a special case of networks. There's many ways to visualize trees. This we might call sort of a layered hierarchical diagram. This one you might have seen before. I think it was David Hillis, the biologist, who made this type of layout famous, sort of a radial of life forms. And this particular diagram has been augmented in bars. I don't know what these bars show, species within each taxa. This is a funny one from an old website called cookingforengineers.com, and it shows the ingredients for tiramisu as leaf nodes, and then each operation for cooking is shown as a successive node. And the last thing we do to the tiramisu is cover it. That's the root node of this tree, right? So the whole thing is a tree. There's a website called treeviz.net, which has more than 300 ways of visualizing trees. It's got thumbnails, it's got references. I think it has maybe links to some of the articles. So, and you can filter all these layout techniques according to whether you're interested in 2D or 3D or explicit or implicit. It's a nice, fun visual way to look at many ways to visualize trees if you're interested in that. One of the ways to visualize trees, which is interesting to know about, is the tree map. So in the tree map, the idea is that the root of the tree is in the outermost rectangle here, and then this rectangle is recursively subdivided to show the children and the grandchildren of the root. And the node reflects something about that node, like maybe the weight or the population. I think it's financial markets. So the root node is the entire thing. That's the entire market, and it's subdivided up into sectors, and then each sector is subdivided up into major corporations. And the size shows something like, I don't know, maybe it's the market capitalization, and then the color might show whether the stock has been going up or down, something like that. Notice that green and red are being used here. That's not nice for colorblind people. And this particular website has an option to switch to a yellow-blue color scale for people who prefer that. Here's another tree map. This is the Philippines. So the Philippines are a bunch of islands separated into 3 groups. So I've got the Philippines as my root node. I've got 3 nodes under that for the 3 groups, and then each of those contains individual islands. And each node here has an area that's proportional to the geographic area of each island. Okay. With my co-author Jean-Marc Robert, we wrote a paper that analyzes the space efficiency of a bunch of different ways of displaying trees. You can take a look at that if you're interested. We have a video that explains it. Okay, so now I get to the part that's maybe more interesting for people. I wonder if I should check the chat. The chat's been very active.
People are sharing lots of cool resources.
Nice. Okay, maybe it'd be awkward for me to read through this now. I like that Emily saying it burns when I guess when I showed the bad colors. Okay, so what I've been doing since 2016. Since 2016, I've been flirting with the idea of dipping my toes into the research area of artificial life. So I started downloading papers and then more papers, and now I have something like 200 PDFs I've downloaded related to artificial life and origin of life. And by the way, if you're interested in origin of life, Santa Fe Institute has a course this summer on origins of life. It's a free course. It's amazing. They have a bunch of other interesting courses. So I've been following that. And I went through all these papers and I looked for charts that looked very nice or maybe not so nice. And I tried to collect the most interesting cases for you. So this is from a paper that does a literature survey, and they're showing a number of papers published in different themes over different years. It's a grouped bar chart, and you see within each theme, they have all these years from 2008 to 2018. So it's kind of weird to be using a color palette for different years. Normally, we don't do that kind of thing. So there are some other ways we could show the same data. I actually took the time to manually enter all these numbers into Excel, and then I was able to generate these pretty easily. So I think these might be better. Even parallel bar charts is not a bad way to look at this data. Within each column, you can see sort of the trend, whether it's increasing or decreasing. And here, you don't even need to have any color palette, right? Okay, another example. This particular paper had this type of grouped bar chart with lots of colors, and the bars are very thin. So to me, this looks like there's the way I would describe this is sort of high spatial frequencies is kind of like vibrating on my eyes, and the colors are kind of saturated. Maybe you can think for a moment about a different way to show this data. So what I thought of is simply drawing line graph, overlapping line graph instead of showing bars. And you could use the same color code. I think this would work fine in this particular case. This paper, so I didn't read most of these papers, but this one for some reason had a rainbow spectrum varying from red to purple or something like that. I don't know why. It seems to be redundant with time. But along the way, the curves become yellow. So we have yellow on white. That's hard to see, right? So that would be easy to fix. This one is using pastel on thin lines on a white background. So that makes the lines hard to see, especially the ones that are closer to white. Like this is not quite yellow. It looks a little bit orangey, but nevertheless, we could use saturated colors here instead. It would make the lines stand out a lot more. This one I really like. So here, if you look at the network here, the edges are drawn with a shade of gray that's close to white. And I think it's well justified in this case because whoever made this wanted to make sure that we could read the text labels on top of the edges. And it looks to me like these text labels were probably positioned manually, one by one. And the result is really nice. This one, so this is from an article co-authored by Eugene Koonin. I mean, if you look up Eugene Koonin on Google Scholar, I think this person has over 100,000 citations. So I'm not trying to criticize anyone's work with these choices I've made, but this particular chart doesn't have the nicest colors. In my opinion, the background colors are a bit too saturated. I think we could get away with more pastel colors and it would look nicer. So here's an example where they did use very nice background colors. You can see the text here is always black, but it's always easy to read. And there's also some very subtle coloring to show different parts of the diagram, maybe to make it more apparent to the reader what the different parts are, or it could make it easier to refer to different parts of the diagram in the caption of this figure. Here's another nice use of background color. So the gray and here the very light red. This red is almost too light, but I think it's quite effective for highlighting subsets of this particular diagram. Okay, so this is an example from one of Emily Dolson's papers, and I think she's in attendance right now. I really like the use of transparency here. You can pretty clearly see red, green, blue, and the transparent red, green, blue, but it gets a little bit difficult to distinguish things here, and I think that just shows the limitations of having overlapping transparent colors. So I think this is probably the best we could hope for when using transparency. It's a lovely example, but if we had like a fourth or fifth category of things, it might get to be too much. This is some visualization of different ways of folding some type of synthetic protein, and the colors show number of contacts. And there's 4 or 5 different colors here. And what struck me is that it's there's actually some points in here that are some shade of red, but it's very hard to see them because they're so tiny. So I took this image and then I edited the colors to get this. And maybe you can see there's some red dots here. You can see that certainly I can see red here quite easily, but there's also some tiny red dots here that were not apparent in the original coloring, because in the original coloring, that color was too close to the surrounding color. So maybe a lesson could be that you want to use colors that are more distinct on smaller objects, and for larger areas, use something that's more subdued, more pastel. This paper presented a number of different cellular automata. I think it was something about searching for different cellular automata rules. And so it had these images. It looked like the colors were chosen randomly. And very often the background color would turn out to be some saturated color. So a simple tweak that could be done automatically would be to detect which color is covering the most pixels and switch that color to be something desaturated. That would make these maybe a bit easier to look at. Here's a very nice visualization of a tree. So the tree of life. What I really like here is along the circumference, you can get an idea of the number of taxa, or maybe it's number of species. And then radially, you have an idea of time. So a lovely diagram. Here's another one. Let's see, this is some type of phylogeny. And I counted the number of labels here. There's 95 labels, so roughly 100 labels here. This way of showing a tree would work very well within a window where we scroll up and down if the tree was too big to fit within a single screen. And here's a similar phylogeny. It's got 96 labels. So again, approximately the same number of labels, but this one's radial. So this is like, I think it was David Hillis who started promoting this way of visualizing phylogenies. And it's interesting to notice that between these two examples, even though they have the same number of labels and they both occupy roughly the same amount of space, in this case, the labels are a lot bigger. They're a lot easier to read. Why is that? So one way we could analyze this is to say, all right, my screen is roughly 10 by 10 inches or something like that. And here I have a circle roughly of diameter 10 inches. So my circumference is going to be roughly pi times that. And so maybe I have pi times more space along which to lay out these labels. Now that's a very rough comparison. It doesn't take into account the fact that I have to waste some space I have to make the diameter of the circle a bit smaller to make room for all the labels, but still these labels are significantly bigger than these ones, okay? But it comes with the disadvantage that now it's harder to read the labels near the top and near the bottom, and it's not so easy to see how to scroll through these if I had a really big tree. Okay, so there's interesting trade-offs between these different layouts. This is one that seems to have become popular in biology. I think this is a phylogeny that was reconstructed, and if I understand correctly, the length of the segments here reflect differences in genetic sequences, and it's lovely. It looks very organic, but I find it unfortunate that there's some space being wasted here, and a lot of the nodes here seem kind of squished together. So maybe there's some way that this layout could be modified to look more like this. And maybe there's a difficulty in this case because maybe it's difficult to determine where exactly the root is. This is something I learned recently in this course I'm taking on Origins of Life. When you try to reconstruct the phylogeny for all of life, it's not always possible to figure out exactly where the root is. So maybe there'd have to be some little adjustment made in the center of a layout like this to reflect that. I'm not sure. 3D bar charts. I found several examples of 3D bar charts and 3D surfaces. Maybe they look cool. The one on the upper left is pretty easy to read, I think, but the other ones are kind of horrible. So this type of data could be visualized instead with a heat map or parallel bar charts or maybe some other approach. Okay, so here's one example I was looking at in more detail. I found this interesting. These are autocatalytic networks, and this is from work by Wim Hordik and Mike Steele. And in this network, we have reactions being shown by white nodes, and the black nodes are chemical compounds or molecules. And so the black arrows show a molecule participating in a reaction. The dashed arrows show catalysis. And here's a larger example where the authors have identified these things called reflexively autocatalytic and food-generated sets, or RAF sets. And they've identified these sort of subsets of the network that are RAF sets. And I stared at this for a long time. I found it difficult to interpret. I found it difficult to check if the RAF sets really are complete. So I played with different ways of modifying this diagram. We have two types of nodes. Maybe you'll agree with me that we could make the nodes bigger to make the difference between the white nodes and the black nodes more apparent. It turns out in this diagram, all the arrowheads are redundant because every arrow connecting a molecule to a reaction is double-headed because the reaction can go in either direction. And the arrows on the catalysis edges are also redundant because catalysis is always going from a catalyst towards a reaction. So we could get rid of those. And so here's a really quick and dirty redrawing of the same diagram. I found it difficult to do curved edges in PowerPoint, so I sort of cheated. I made the catalysis edges thicker and in the background. And then it occurred to me, maybe it'd be interesting to put all the reactions in one column and all the molecules in a different column. So that's what I've done here. So this sort of emphasizes that the network we have is bipartite. All the edges go between two disjoint subsets that partition the nodes. And then I tried drawing the RAF sets. So that was a bit of a pain, but these are the different RAF sets. And if I show all of them at once, I think this is getting close to the limit of what we can understand. So I don't know, I think there's various advantages and disadvantages with this. I do find it easier to check that each RAF set is complete. So for each RAF set, you can check all the reactions in the set are connected to molecules that are also within the set and also connected to their catalysts within the set. And I find that type of thing difficult to check here. So anyways, maybe that's food for thought. Okay, how are we doing for time?
Well, you have about, sorry I took over for Juniper, you have about 13 minutes left. If we go over a little bit with questions, that's okay, but we should roughly try to keep it to 4 o'clock.
Okay, so I could stop here with the content. Maybe people have questions they want to ask.
And if you want to do that, we can handle that one of two ways. Either people can ask the questions in chat, or they can, if we have the hand raising enabled. I'm not sure if I see that. Yes, under more in the
Okay.
participants, you can raise your hand too.
Okay, so I can see if someone raises their hand.
Should be able to. We can test that out. I can. Oh, maybe we have that disabled. Oh, okay. There's a hand.
Okay.
Okay, great.
I don't know how to say the first name, but Ackles?
It's okay. I didn't have a question. I just wanted to see if the raising hands worked.
Cool.
That's helpful. Okay, so if anybody does have a question, feel free to raise your hand. And if you, by the way, these are being recorded. If you don't want your voice to be recorded asking a question, you can also just type in the chat and then we can read the question out loud.
Okay, Benjamin Emery.
Hi, okay, yeah, I'm actually kind of asking this question on behalf of, I'm sorry if I say your name wrong, Niklos Tepes, who narrowly typed it just before me. But I'm wondering what you think about redundancy in general and if it's always bad for visualizations or if there are certain instances where having information conveyed in multiple ways might be useful.
That's a very interesting question. I don't think it's always bad. I haven't thought about it enough. So one example I remember seeing is a line chart. Let me see if I can approximately show you what it looked like. I need to hide these windows now. So I've seen line charts where the color of the line actually varies continuously to show you the Y position. It was something like this. So imagine just a single line where the color under the line varies continuously and becomes more bright as the curve gets higher. Now, is that useful? I don't know. Are there other examples where it is useful? Probably, but I haven't thought about it enough. I think it's a very interesting question. You know, on that topic, maybe some of you are familiar with Edward Tufte's work. So Edward Tufte has written these classic books on data viz. And one of the things he complains about is people who waste ink. And he talks about optimizing the ink to data ratio. And maybe I can pull up an example on Google Images. Chart junk, I think is what he calls it, wasted ink and chart junk. Here's a great example. Okay, maybe this isn't the most politically correct example, but you've got here the price of diamonds changing over time, and it's being shown with this evocative image of a woman's legs. Can I make that bigger? Yeah, so this is an example of what Edward Tufte would call chart junk. And he criticized this, but the thing about this chart junk is it's entertaining. So if you're publishing this in a magazine or newspaper, some people will find it intriguing. Another thing that's been found in recent studies is this makes the chart much more memorable. And sometimes adding something as silly as a dinosaur in your chart, even if it has nothing to do with the data, it can help people remember what was being shown in the chart because it makes it so peculiar. So I didn't exactly answer your question, but I sort of found something else to talk about. Okay, has someone else got their hand raised?
Yes, and by the way, the order that the people are shown in the participant list is the order that they raised their hand in.
Wonderful, so I think Adil is next.
Mm-hmm.
Sorry, was that my name?
Hello.
Yeah, ADIL, Adil, I think they had a question.
Yeah, that's me. It's me, yeah. It's me.
Great, please ask your question.
Yeah, I think it was a really kind of like an enlightening tutorial actually, you know, and it tells us so many things. I was wondering about one thing, you know, that how to, let's say, like if you have multivariate high dimensional data, how to visualize that on low dimensionality grids actually. You know,
visualize
like
on what?
Do you want me to repeat?
Yeah, because the audio is cutting out a bit.
Hello? Yeah, I just wanted to ask that, you know, how to kind of like visualize high dimensional multivariate data on low dimensionality grids, like in 3D or something, you know, some techniques or principles or algorithms or mathematical kind of like constraints or principles for that might be good. Any pointers to that actually?
Yeah. So this slide sort of lists the techniques I'm aware of.
Okay.
So principal component analysis, multidimensional scaling, T-SNE. I think these are part of a larger family called dimensionality reduction techniques. And usually they're used to reduce many dimensions to 2 dimensions. You could probably reduce them to 3 if you wanted to, but maybe that's not advisable. And I also showed parallel coordinates, scatterplot matrix. There's some interesting variations on scatterplot matrix, like there's a way of visualizing networks using a matrix of metrics, and it's called graph dice. If you search for graph dice as one word, there's a video that shows that. Sometimes your matrix is really big because you have so many variables, and there's a way to reduce it to a smaller matrix, and that's called scagnostics. And if anyone asks me in the Slack, I'll point them to a reference for that. Yeah, and we have a paper called SPLOM, which proposes another extension to this. But it sounded like you were talking about 3D. I would encourage you to try to visualize stuff in 2D, because there's actually many studies that show that 3D is detrimental. It creates all sorts of problems. It's difficult to interpret things in 3D. There's occlusion. It's more complicated.
We then had a question from the chat, if we want to skip over there for a second, and then we'll come back to the other hand raised question and then see how much time we have left after that.
Okay, let's see. I guess in the chat, it would be fair for me to go back to the oldest question.
I think Leo's question here about stress majorization algorithms should be the most recent one.
Okay, so Leo is asking if I have a demonstration of stress majorization, not one that I can run easily. I do have some Java code somewhere, and I could dig that up if someone really wants it. But if you look at that article I pointed to in the slides and look at equation 12, see if you can understand that. And if not, then I'll dig up more information for you. So yeah, is there someone else in the chat I should respond to?
I think that was the only one that came up during the question and answer session.
Thanks. So R. Zimin has a question.
Yeah, it's Robert.
Wow. Hi. So Robert's actually an old student of mine from many years ago.
Yeah, fantastic presentation.
Thanks.
So one thing I noticed is missing in your discussion here is dynamic visualizations of high-dimensional data, which I find very interesting for the fact that we now have computers that can do this more easily. All of these older techniques are sort of rooted in the Edward Tufte and John Tukey, exploratory data analysis type stuff. So what would you say in terms of like useful and interesting ways to look at high-dimensional data through interactivity? Okay,
so that's a great point. So it is true that Tufte and sort of the older literature doesn't talk about animation and interaction. You can imagine all sorts of ways of using animation to show different variables. And it turns out some of the ways you could do that don't actually work that well. I think there's an article called Animation Does It Help, which does a survey, and it sort of points out the problems of using animation. But there are other ways you can use animation which are actually very good, very effective. If you're showing the user a transition between 2 different views of data, it's very useful to show them a smoothly animated transition instead of sort of an abrupt, discontinuous snapping from one view to the other. And there's work that's been done on smoothly animated transitions. Another technique which is kind of interesting is called RSVP. So maybe you know RSVP for répondez s'il vous plaît, when you get invited to a party. RSVP also means rapid serial presentation, rapid serial visual presentation. So there's some older articles on that, and the idea there is, imagine if you could hover your mouse cursor over a folder or an icon or maybe a glyph, and then very rapidly you would see a quick animation loop of the contents of that thing. And just by staring at it for a moment, you could decide if it's interesting, if you want to dig in further or not. And so related to interaction, there's all sorts of new interaction devices which are now very cheap. Things like Magic Leap, if you want to track your fingers in 3D. you know, virtual reality and augmented reality are probably going to make hand tracking more common and easier to work with. So it's possible that that could lead to some new interesting ways of navigating faster through data. It's kind of unfortunate that keyboards and mice make very little use of all the degrees of freedom of our fingers.
Yeah, thanks for that. The other part of the other question I had was kind of related to the chart junk comment. So yeah. I find that a lot of illustrations in scientific material are impressive looking and ultimately not very useful. So especially a lot of the complicated like network graphs in computational biology and stuff like that. So do you have any examples of, you know, especially good looking, beautiful, useless visualizations or actively misleading visualizations in the same sense as, you know, the old book, How to Lie with Statistics?
I used to be very interested in visualizing large networks for biology and things related to that. And there was 1 or 2 years when I went around to a bunch of different labs trying to convince biologists that they should collaborate with me and visualize their big networks. And no one was interested in that. I think a lot of computational biologists, they have big networks, but they don't need to visualize them all that much. They might be interested in tiny parts of the network, or they might run algorithms on the networks, but they don't have a burning need to visualize them. And I guess I can speculate as to why. When you have a big network and you visualize it, often it looks like a big hairball.
Exactly. I mean, that's part of the problem.
And that reminds me, Ben Schneiderman had this famous paper where he said that when you visualize data, you should always start with an overview, and then you should give the user ways to filter and zoom in and get details. And recently, some people have started arguing we should also allow the reverse. If someone has a big data set, instead of showing them an overview, allow them to start with a search for one single data item that interests them, show them that one little data item, and allow them to expand outwards from that. So they only look at the things that are interesting to them. So great question. I think we've just run out of time.
That is right. So it's about time to wrap it up. I want to thank you very much for giving this presentation. I think we all really enjoyed a lot of it, but especially that sort of critique of ALife paper visualizations. Susan is asking how we can save the chat. I'm not actually sure if we can save Zoom chat. I can look that up real fast, but I would encourage everyone, either if you had something else you wanted to talk about, if you wanted to post any links, or if you had any other questions that you wanted to ask, do feel free to go over to the Persistent channel on Slack called Tutorial ALife Viz 2020. That'll be there for, as long as the Slack workspace is open. Okay, and then we have a comment that says Zoom chat is saved automatically with the recording. So we'll see if there's, any way that any of that could be shared. But thank you very much.
I just shared a link with a survey. It's a 3-question survey. If you take the time to answer the questions, that'll be really helpful. Thank you.
All right, so I'm going to just close the room now so everyone knows. Thank you all for coming.